Hi everyone. In this lecture we will be seeing two important concepts of process management. The first one is about operations on processes and the second one is interprocess communication. In case of operations on processes, it is nothing but whenever a process is running in the system, it will be working on two major operations. One is your process creation and termination. When the process enters into the system, it has to be created by the operating system, and the same way when it completes all its execution, it has to be terminated. So that is the objective of this session. And the second one is about the interprocess communication. So we know that whenever a process is running in the system, one process may depend on another process for resource sharing or information sharing. So in that case, the process has to get communicated with each other in order to run its execution parallelly. So interprocess communication is a major factor for the process execution or the concurrent process execution. So let us move to the lecture. The topic is operations on processes. We know that in most of the systems, the processes are executed concurrently. So the concurrent execution of the process is needed because that the process are dependent on some other process for information sharing or data sharing and resource sharing. In this situation, the processes are created and deleted dynamically. So during the process creation, a process may create several new processes. So consider the following scenario, and here this is the process which is creating the new processes. Then this process is called as the parent process, and the process which are all created by the parent process are called as the child processes. And these child processes may in turn create n number of child processes. So it will form as a tree. So the process creation in the system will be something like a tree-like structure, where a parent process is creating child process and the child process is creating n number of child processes. And in case of process creation, a unique identification number for each process is given. So this is a unique number where each process is identified, and normally this will be like an integer number. So here we can see the tree of processes on a typical Linux system. So here init is the root process which is created for the entire process tree. So this init can create any number of subprocesses. So the login process is used for maintaining the clients which are logging onto the system. And here there are two processes created which are like kthread and sshd. Kthread will be taking care of the operations that are carried out by the kernel. So it in turn creates processes like khelper and pdflash. And also this SSHD is a process where it manages the client side operations, and this in turn creates SSHD and TCSCH. So these are all something like related to the client server operations, and this is done with the help of secure shell, that is SSH. And in case of this login, it is again creating an bash command line interface which is used in the Linux operating system. And this in turn creates like two other processes, which is your PS and Emacs. And PS is used for listing all the processes which are running in the system. And Emacs is nothing but an editor in the Linux operating system. So in this way, one process can create any number of child processes for various operations. Whenever a process creates a new process, there are two possibilities for execution exist in the system. The first one is that the parent continues to execute concurrently with its children. So the parent is not running separately, instead it is continuously or concurrently executing along with the children. This is one possibility of executing the new process. And the second thing is that the parent waits until some or all of its children have terminated. The same way, two address space possibilities are available for the new process. One thing is the child process is a duplicate of the parent process, and it uses the same memory space, the program and the data as like the parent. Or the child process may have a new program loaded into it. So these are the two address space possibilities for the new process entering into the system. So now let us see for the fork system call for creating a separate process using the Unix fork command. So the fork command is used to create a new process. So these are the various header files which is used for creating the fork system call, and UNISDD is something like Unix standard header file. So here PID is the variable which is created for storing the process ID number. And this is initiated along with the fork system call. Whenever the fork is created, it will create the process along with the ID. That ID will be assigned with the PID. And in order to check whether it can create or not a new process is based on the value of the PID. If the value of the PID is less than 0, then the process fork is getting failed. So that is a standard error. By this, when it is less than 0, we cannot create a separate process. And we have to check that whether any other process is running in the system. In order to check that, normally whenever a child process is created, its PID is assigned with 0. So when it is 0, the child process is getting executed. So that this AEXECLP is a function which is used to use the existing address space of the parents. So this will be done if PID is equal to 0. Otherwise, the parent process has to wait until the child process is getting executed. So if it is 0, the child process is created and it will be getting executed. Otherwise, the parent has to wait until the child process is getting its execution. So this can be done with the help of the wait function. And after the child complete, one the parent will can resume its operation and it can continue. So this is the way we can create a separate process using the fork system call based on the PID value. If the PID value is less than 0, that is a system error. If it is equal to 0, then a child can execute its operation and the parent has to wait if the child is executing. So this can be understood with the help of this diagram. So as we discussed here, the parent is creating the fork system call and the PID is assigned here. So based on the PID value, the separate process is created. If it is equal to 0, then execute command is used to use the existing address space of the parent. And after the child exit, it will go for the wait command. So this wait command is accessed by the parent. So the parent has to wait until the child is getting executed. And the parent resumes its operation of the after the child execution. So, and the other operation of the process is process termination. We have seen how it has been created. Now we can see that how it can be terminated. When the process finishes its execution of its final statement, so it asks the operating system to delete it by using the exit system call. So all the resources which are allocated to the processors, including the physical and virtual memory, open files and IO buffers, are deallocated by the operating system. So, a parent may terminate the execution of his children for a variety of reasons. As we have seen that a process may create any number of child processes. In that case, a parent may terminate the execution of his children for a variety of reasons. The first reason is that the child has exceeded its usage of some of the resources that has been allocated by the process to it. Otherwise, the task assigned to the child is no longer required. So, we can terminate the execution of the children. Or the parent is exiting and the operating system does not allow the child to continue if its parents terminate. In that case also, the parent may terminate the child. And some systems do not allow a child to exit if its parent has terminated. In that case, what happens is that the process terminates abnormally or normally. So all its children are also has to be terminated. So this phenomenon is called as cascading termination. So that means whenever a process is terminated, so the child process has to be terminated. So the child process may be terminated normally or abnormally. So in that case, the child is removed by the process forcibly. So this phenomenon is called as the cascading termination. So the exit is a function which is used for process termination with the value 1. So if exit of 1, so we can understand that the process has been terminated. In case that when a child is executing, so in that case the process has to wait after getting the status of the child, it can terminate. Otherwise it has to wait. So the exit status may be done only after the status of the child process is received by the parent process. So this is what about the operations on processes. Interprocess communication. What is this interprocess communication? It is a mechanism that allows the processes to communicate with each other. It is called as interprocess communication. For this, first let us understand that why the process needs to communicate with each other. We know that more number of processes are executing in the system at a single time. So that means all these processes are concurrently executing in the system. So during that time, these concurrent processes may be either independent processes or sometimes it may be cooperating processes also. In case of independent processes, the process will not depend on other process for sharing of information or resources. In case of cooperating process, the process may depend on other process for information or for resources is called as cooperating processes. Let us understand these things in detail. Independent processes is the one which will not be affected by other processes. At the same time, this independent processes will not affect other processes execution. So it won't be affected or it will not affect. Both things are different. Also, the process does not share any data with other process which is called as independent. So always it is a separate process which is running independently without the intervention of any other processes is called as independent process. In case of cooperating process, it can affect or be affected by other processes executing in the system. Here dependency is occurring. Also, any process that shares data with other processes is called as cooperating process. Now let us understand the reasons for allowing process cooperation. So these are the 4 important reasons for allowing each process to communicate with each other. One is information sharing, computational speed up, modularity and convenience. This information sharing allows the piece of information of one process with the other process. Sometimes user may require to share the information with the other user. Also, one user may require the information which is used by the other user. The best example for this is Google Sheet. We know that this Google Sheet can be used by multiple users at a time. This is an attendance sheet. Here we can see that there are 2 persons using this Google Sheet. So one person is editing, at the same time the other person can also edit. So here you can see that this is one user where they are editing the data. So it is getting entered. At the same time the user here is also editing the data. So that data will also be used at the same time. So this is the use of information sharing. The next one is computational speed up. If a particular task is to be executed by the process, if the process wishes that it want to increase the execution speed, so the process can be divided into number of tasks by the process in order to increase the computational speed up. Also, the task may be divided into subtasks in order to execute these process or subtasks in parallel. That's why automatically the computational speed up for the process is getting increased, like what we have seen in the Google Sheet. So when one data is filled by a single user, instead multiple user can fill up the data at the same time, so that the task is getting executed parallelly. The third thing is modularity. So we know that the system may be designed in a modular fashion, so that the modules can, each module will work on a different aspect, so that the system function works as a separate threads or processes. The last one is convenience. Even an individual user may work on many tasks at the same time. So that time the user will feel convenient in order to share the data between the 2 systems. So for instance, a user may be editing, listening to music and compiling in parallel what we do the normal task in our daily routine. Sometimes we work on a sheet, at the same time we will be hearing music, at the same time we will be opening our email for the mail checking. So all these things are happening in a concurrent fashion. That's why this interprocess communication is allowed, or the process cooperation is allowed for these 4 different reasons. Now we have understood that what is a cooperating process. A cooperating process is the one in which the process is depending on other process for its execution. Then we can say that it is an cooperating processes. So these cooperating processes requires an interprocess communication which allows the exchange of data and information. So there are 2 models of interprocess communication. One is shared memory and the other one is message passing. First, let us understand that what is this shared memory concept. In case of shared memory concept, there will be a common memory shared between 2 processes. So inside the computer memory, there is a common space given for this memory, and each process will communicate only in that shared memory. So in here, the process can access the other process updation. So whenever a process is updating, the other process can view the updation. So that is what called as the shared memory concept. There are few important things to be noted down in the shared memory concept. In the shared memory concept is faster than the message passing model. And also the system calls of the operating system are used only for establishing these shared memory regions. And after that, there will be no need of any assistance from the kernel is required for the processes. Instead, the process itself will take care of the shared memory. And if any synchronization issues or the memory management issues to be handled by the shared memory is taken care purely by the processors only. So let us understand the shared memory concept using the producer-consumer problem. So in case of producer-consumer problem, the process produces information and that is consumed by a consumer process. The example for this producer-consumer problem are accessing images or files using a web browser. So where the client is requesting for an image from the web server and the client is getting responded by the web server after giving the images which is required by the user. And the compiler which is producing the assembly code can be consumed by a assembler, and the assembler in turn consumes the object modules consumed by the loader. So these are the few examples for understanding the producer-consumer problem. There are two types of buffer in case of producer-consumer problem: unbounded buffer, unbounded buffer. In case of unbounded buffer, there is no limitation for producing and consuming the items. The producer can produce n number of items and the consumer can consume n number of items. Also that the producer will not wait for the consumption of the consumer. At the same time, if the producer is not producing, the consumer has to wait until the producer is creating at least one item in the buffer. So there is no limitation. Also, in a case of bounded buffer, the producer can create the items based on the buffer size. Here buffer size is fixed. At the same time, the consumer can consume based on the buffer size only. If there is no item, and the consumer has to wait once again for accessing the item. In both the cases, the producer or the consumer, either one can run at a time. So if the producer is producing, the consumer cannot consume. And the consumer is consuming the item, the producer cannot produce an item and keep it in the buffer. This is what the concept between the unbounded and unbounded buffer. So here we can understand that these are the number of items produced by the producer, and a buffer is required and a communication link is also required for sending the items in the buffer, and the consumer will be consuming the items from the buffer. Now let us consider the producer-consumer problem using the bounded buffer size. So the bounded buffer size is 4 is fixed here, and now the producer can produce item number 1, 2, 3 and 4. So when the producer tries to consume more than the 4 item, what happens is that the buffer cannot occupy because the buffer is full, and at the same time the consumer can consume the item number 1, 2, 3, 4 if it is available in the buffer, and after that the consumer, if trying to consume the information, what happens? So it cannot consume because there are no items available in the buffer. Now let us see the algorithm for the producer-consumer problem. So this is the space or the region of the memory shared by the producer and the consumer process. So what will be available here? So since it is a bounded buffer algorithm, here the buffer size has to be defined. So the buffer size is defined as 10. And also we have to define what is the structure of the item which is going to be produced. So for that we need a structure type, and item has been declared here. So after that, the structure variable buffer has been defined with the buffer size, and we need two variables here, which is your in and out. So this in and out are called as the counters for the producer and the consumer. So the producer will use the in counter and the consumer will be using the out counter. So these counter will maintain the buffered items whenever a producer is producing and whenever a consumer is consuming. So this is the region of the common region where the producer and consumer is sharing. Now let us move on to the producer process, which is using the shared memory. So the producer will have the variable called as item next produced, and it will be checking a condition that while true it will be using a loop. Using that loop it will produce an item. So the item is next produced. So before that it has to check whether the in plus 1 modulo buffer size is equal to out. So what is this? So this will check the size of the buffer, whether the buffer is exceeded for producing or not. So that we have to check before creating the item. So that is done inside the loop again. So this checking, let us assume that here we have like the initial buffer size is 4 and the buffer which is using the count variable is your in and out. So the in variable is having only 0, initially assigned with 0. So let us assume there is no items in the buffer. So in that case it is 0 plus 1 modulo 4 is equal to 0. So the condition which here it checks using the while loop is not true. So since it is not true, instead of do nothing it will produce an item. If suppose in this case it is 1 is equal to 1, means that the buffer size is 4 and the item which is already produced is also like 4, means that it cannot produce an item. So that is what the checking done over here. So and after that what happens is that the next produced item is kept in the buffer location based on the counter, the index value, which is nothing but your counter. So buffer of 0 will be kept with the next produced item. And after that the in counter has to be incremented by 1. So here it is done with in plus 1 modulo buffer size, which is nothing but, now there is no item as we discussed earlier. It is 0 plus 1 modulo 4. So it is nothing but your 1 only. So the item produced is 1. So the same way how the consumer have the concept defined is item is equal to next consumed. Here the item which is going to consume is next consumed, and here the true condition it will be checking with in is equal to out, whether the in and out are equal. If so, we have to do nothing because already it is consumed and it is equal. So there is no items has been consumed by the consumer as of now. So we are checking that 1 is equal to 0. Produced item is 1 but consumed item is 0. So instead of doing nothing, it will go on consuming the item. So the next consume is equal to buffer out. So the buffer out is 0 and it will be taken by the next consumed. So after that the out counter has to be incremented by 1. So out is equal to out plus 1 modulo the buffer size. So now what happens is that your out is incremented by 1 so that we are consuming with one item. So in this way the producer and consumer will produce and consume the item based on the buffer size which is bounded. The first model what we have seen is called as the shared memory model. So here we will be seeing about the message passing. So what is this message passing model will do? So here you can see that there are lots of messages available and that messages can be taken up by the processes. So there will be a message queue and the message queue will be containing the messages and those messages can be accessed by the processes. So this message passing is applicable to smaller amounts of data. If the amount of information to be shared by the process are smaller, then we can go for this message passing method. Otherwise, if it is the data is large, we can go for the shared memory concept. So also, it provides a mechanism for allowing the processes to communicate and to synchronize their action without sharing the same address space. So likewise in the shared memory concept, which is sharing a common memory space, so the message passing will not do. So instead that it allows the process to communicate and to synchronize their actions only. So it will not share any common memory space. Also, it is useful in the distributed environment where the communicating processes may be residing on a different computers connected by the networks. So in those cases, the message can be passed between one process and the other processes. And there are two important operations in message passing, which is your send message and your receive message. So one process can send a message to the other process and the other process can receive the message from the process which is sending the message. And the message sent by the processes may be fixed or variable size. So what is fixed size and variable size? If suppose the message size is fixed as 100 characters, so it is called as fixed size. If there is now not like something like a constraint, then we can say that it is a variable size messages can be sent. So there are some difficulties in fixed size and variable size messages. So in case of fixed size messages, the system will have an implementation like easier. But when it comes to the real time, the fixed size program may have lots of issues. But in case of variable size, the implementation is tougher and the passing of messages is getting easier. These are some of the observation of the fixed size and variable size messages. And the communication link is required for sending the messages from one process to the other process. For example, let us consider that process P is sending a message to process Q and there needs a communication link. Through this communication link only the data can be, the messages can be transferred from one process to the other process. There are three ways of establishing the communication link. So this can be done by using a direct or indirect communication, synchronous or asynchronous communication, and something like automatic or explicit buffering. Naming. Naming is the method where a process can communicate with each other by some reference. And it uses the direct or indirect communication. So first let us see naming using direct communication. As we have seen earlier, message passing contains two operations. The first is send and receive. A process can send the message to other process, and at the same time a process can be receive message from other processes also. So the send message here contains the processor name along with the message, so that it is understood that sending a message to process P. So likewise, receive operation. So the receive operation is having the format, it is receive Q comma message, which means that receive a message from process Q. In case of naming, the communication link will be having the following guidelines. A link is established automatically between every pair of processes. Whenever a process needs to communicate, that pair of process has to establish the communication link, and it is done automatically. A link associated only with two processes. A link cannot be associated with more than two processes. And the third thing is that between each pair there should be existing only one link. Not more than one link is permitted. And this thing what we have seen now about the naming concept is symmetry in nature. That means each processor is identified with their name. So that name is used for the communication, so that the process is identifying each other without any problem. In case of asymmetry addressing, what happens? So there is a concept like asymmetry also. What happens in asymmetry addressing? In case of asymmetry addressing, the send operation will be having the process identification. So whatever message is sent, that is identified to which process it has been sent. But in case of receive operation, the identification is not given. So that means that it will be any process can be receiving a message from the other processes is possible in case of asymmetry addressing. In indirect communication, the messages are sent to and received from the mailboxes or ports. Each mailbox has an unique identification here, and the processes can communicate using different mailboxes. So the send message is sent here using the identification A, that means from which mailboxes the message has been sent. So the process identified that the message has been received from a particular mailbox. Here send a message to mailbox A is the indication of this send A comma message. So when we say that it is receive A comma message, receive a message from the mailbox A is understood. So what about the communication link here? So the link is established between the processes only if they have a shared mailbox. Otherwise it cannot be shared. Also, the link may be associated with more than two processes. In the previous case of direct communication, the link can be established with only pair of processes. But here the link can be associated with more than two processes. And between the processes, different links may exist. But in direct communication, only one link can be established between the processes. Not more than one link is permitted. But here the processes can have or may have different links. The mailbox may be owned by a process or by the operating system. In naming concept, we have seen that message passing can be done using direct and indirect communication, which uses the symmetry or asymmetry addressing. The second one is synchronization. Message passing may be blocking or non-blocking also, and this is also called as synchronous or asynchronous message passing. So in synchronization, there are two things which is for sending the messages. One thing is blocking send, other one is non-blocking send. In case of blocking send, the sending process is blocked until the message is received by the receiving process or by the mailbox. And in case of non-blocking send, the sending process sends the message and resumes the operation. And the second thing is that it is about receive operation. In receive operation, there are two things again. One is blocking receive, other one is non-blocking receive. In case of blocking receive, the receiver blocks until a message is available. In non-blocking receive, the receiver retrieves either a valid message or a null message. So these are the four different operations in case of synchronization. So these can be used in different combination of send and receive are possible here. The next one is buffering. Whether the communication is direct or indirect is considered in case of your buffering. So and the message is exchanged by communication process reside in a temporary queue. And there are three ways of implementing this buffering concept. One is your zero capacity. In case of zero capacity, the queue has a maximum length of 0. Thus, the link cannot have any messages waiting in it. Whatever available, that has to be sent. In this case, the sender must block until the recipient receives the message. The sender cannot unblock until the receiver receives the message. In the second one is bounded capacity. In bounded capacity, the queue has a finite length of n, and the queue is not full. Then new messages can be sent. The message which is placed in the queue and the sender can continue execution without waiting. But in case that if the queue is full, then we say that the link's capacity reached its finite state and it cannot send the message, so it has to block until the space is available in the queue. The third one is unbounded capacity. The queue length is potentially infinite and any number of messages can wait in this unbounded capacity, and the sender never blocks of sending the messages. There are three ways of implementing this buffering. One is zero capacity, bounded and unbounded capacity. In zero capacity, we know that there is no buffering is possible. And in case of bounded and unbounded capacity, automatic buffering is possible. One is have an finite length and the other one is called as infinite length in case of your unbounded capacity. That's all about the inter-process communication using the shared memory concept and message passing. That's all about the lecture. Thank you.